So we have been saying all along that is the thing as vertical, makes changes in vertical motion, and that there are no horizontal causes to create a horizontal effect. In other words, a horizontal acceleration. That language is awkward. You felt it. I've known, yeah, you knew it all along that is not great language. So I'd like to polish the language a little bit, and I'd like to agree on what's called causes that affect motion. Causes match to their effects. In other words, are proportional to. A bigger cause creates a bigger effect. A smaller cause creates a smaller effect. This is not news. Changes in motion. How do I know that something happened? Means something changed. If something changed about my motion, the equipment we have to talk about that is acceleration. There was some velocity, and something about it has changed. Either it's in a different direction now, or it's a different. In the motion. When we say a cause, well, no idea what just happened. I think we're back. Instead of pushes or pulls, I'd like to give the formal name for that kind of thing, an interaction of something with something else. Acceleration is a vector. That proportionality implies that force must also be a vector. Now, if two people push the same thing, to talk about the total net effect that they're going to have. Again, this is not really news. I'm just going to write it in formal math. That's it. Sigma, mathematical notation. Add up all the F force, the net force, the total force, the sum of all the forces. If forces are vectors, sum of all the forces means like vector components or Pythagorean theorem, stuff like that, that we did last week when we started talking about vectors. What is the thing that tells me how much effect I get for a given cause? You want to push this wheelie chair across the room. So you apply a cause, you push on it, and you get some effect. You cause it to move, you get some acceleration. If I'm sitting in it at the time, and you push the same way with the same cause, the same force, do you get less, equal, or more effect? Less. What changed? If I'm sitting in it versus if I'm not? The weight. Absolutely. Weight is a tricky thing. Because if I go to the moon, I have a different weight. But if I take my body to the moon, what is the same? How much matter is represented by that object, which we said we were going to measure with mass. Absolutely. All right. So the force that's applied should be force. The bigger thing is what you told me. So the equal sign goes this way. To get a given acceleration or a bigger mass, we need a bigger force. Again, how many of us have seen this before? Does it feel non-intuitive at all? This always felt sort of like, well, yeah, all right, to me. Textbooks make a big fucking deal out of it. And to be fair, we will make a big deal out of it. This is Newton's second law, and we are not getting away from it. It will continue to like knit at our heels for the entire rest of the semester. We're going to become really good friends, or at least frenemies, with Newton's second law. You will get tired of me saying Newton's second law.
Sorry, do you mind going up to the top for like 2 seconds? Real quick. I'm sorry. Thank you.
There we go.
Thank you.
Wow, that took forever. Okay. So
Yeah, you want to go back?
we skipped Newton's first law. And the reason for that is that I think Newton's first law doesn't really deserve to be a law on its own. If, according to the second law, if we follow it along, the sum of the forces is 0, what can you tell me about the acceleration? 0. Congratulations, that's Newton's first law. We just don't say it that way. But that's all it is. What we say is the converse of the logic. Like, think about symbolic logic. An object in motion or at rest remains that way unless we do something to it, unless we interact with it, unless somebody pushes or pulls on it. An object at rest remains at rest. An object in motion remains in motion because. Anybody remember the Bill Nye the Science Guy show? Next time, it's too late. I can't pull it up. I really want to, but I won't. The theme song, the intro music, you know? Inertia is a property of matter. It's the property that tells you how strongly an object wants to keep doing what it's doing. The first law, which is to say an object remains doing what it's doing unless we go pick it, is often called the law of inertia because it's just objects doing what they were doing, which is what inertia talks about. The way we measure inertia, mass. The more mass you have, the harder harder it is, the more we have to push to create an effect. We built inertia into Newton's law already. We knew it should be there. We didn't know it was called inertia, but, or maybe we did already.
Wait, what's the measurement?
Sorry?
What is that?
Inertia?
Yeah.
Is the tendency of matter to preserve its state of motion. Whatever it's doing, it wants to keep doing, especially the bigger it gets. Sort of loosely, this is Newton's first law. Newton's third law, since we're on the subject, has been co-opted a little bit by Hollywood and the greeting card industries. Every action has an
Reaction.
a reaction. What kind? We want to be precise about it. If I'd like to add this word here. Interactions. If I go push on a thing, in order for that interaction to be fully symmetric from the desk's point of view, it's sort of like the desk pushed on me and I just didn't go anywhere. That I had my feet planted and the desk didn't have its feet planted, so it kind of bumped into a wall and bounced off. So in order for an interaction between any of us to be perfectly symmetric and for the physics to apply, no matter whom you ask what happened, if I interact with you, by definition, you're interacting with me. That's how interaction works. And that's the thing, you and me, it's the same two people interacting, right? If I interact with John, and then John interacts Newton's third law pair. If two objects interact, then those two objects interact. If object one acts on object two, then necessarily object two acts on object one with equal and opposite force. It's true, the equal and opposite piece needs to be there. But we have to be more precise. And we're out of time. This, just now, that was the entirety of chapter 4.
What does that say? With what forces?
E plus O, equal and opposite.
Oh, okay. Thank you.
It's the part we already knew, so I abbreviated it because I got lazy and because I'm watching. All right. So I have a demo activity. We have negative 2 minutes. Have a good night. Thanks, everybody. we'll do the demo.
The reaction to it, or?
No, I'm going to change it. We'll do it on Thursday.
Okay. And that last one was Newton's third law.
It is. Yep.
Okay.
That's a good call. Newton's third law. Thanks, everyone.
Thank you.